Now in this class we will be seeing one type of amplitude modulation which is known as double sideband suppressed carrier. As we know that the spectrum of standard AM wave is full, that is, we will have the carrier, the upper sideband and lower sideband. So all these are completely represented in the standard AM wave. So if we see the spectrum of AM wave, so we have the carrier component. This delta function will be carrier component. We have upper sideband and lower sideband. So we have all the three components in standard AM wave. So hence it is called as double sideband with full carrier. We are having two sidebands, lower sideband, upper sideband, and also carrier is present in the standard AM wave. But as we have seen in power calculations, 2/3 of the power is lost in transmitting the carrier, and only 1/3 of the power is used to transmit the sidebands. So when we have represented this total power PT is equal to PC into 1 plus mu square by 2, where PC is the power of carrier and mu is the modulation index. So from that, we have observed that when mu, that is modulation index, is 1, so 2/3 of the power is used to transmit the carrier, and only 1/3 of the power is used to transmit the sidebands. That means the transmission efficiency is only 33.33%. Since the information is present only in the sidebands, and the carrier is simply used to make sure that the message signal is traveled for longer distances. So the power that we are using to transmit the carrier is wasted, and the power we are using to transmit the sidebands is only useful at the receiver side, and hence the transmission efficiency is only 33.33%. So this transmission efficiency is defined as total sideband power divided by total transmitted power. So when we take mu is equal to 1, it will be 1 by 3, which is 33.33%. So this is the main drawback of standard AM wave, because we are only using 1/3 of the power to transmit the message signal. That is, the required information is being transmitted by using only 1/3 of the power. So to overcome this drawback, what we can do is we can suppress the carrier component from the modulated wave, which will result in double sideband suppressed carrier modulation. So since here in standard AM wave, as the carrier is occupying more power, so to overcome this drawback, we can suppress the carrier component. That means we can remove this carrier component from the modulated wave, and we can transmit the AM wave without this carrier component. So this form of AM is called as double sideband suppressed carrier. That means we are transmitting both the sidebands, lower sideband and upper sideband, but we are suppressing or removing the carrier component. So hence, by suppressing the carrier, we obtain a modulated wave that is proportional to the product of carrier wave and message signal. So if you remember the standard form of AM, so it is expressed as AC into 1 plus Ka m of t times cos 2 pi fct. So if we look at the standard AM wave, so it will be this carrier plus product of the message signal and carrier signal. So standard AM wave has two components. One is the carrier alone, that is AC cos 2 pi fct. This is the carrier component, and the other term contains the product of message signal and carrier multiplied by some scaling factor. So this is the standard AM wave. So coming to the DSB, so we can remove this component, and hence it can be expressed as simply the product of the message signal and carrier signal. So hence, by suppressing the carrier, we obtain a modulated wave that is proportional to the product of carrier wave and message signal. When coming to the time domain description of DSB, so double sideband suppressed carrier wave can be expressed as S of t is equal to C of t into M of t. So here S of t is the modulated signal, C of t is the carrier signal, and M of t is the message signal. So its time domain description is simply the product of carrier signal and message signal. So since it is simply the product of message and carrier signal, this modulated wave undergoes a phase reversal whenever the message signal crosses 0. So since it is the product of message and carrier signal, so whenever this message signal will go to the negative values, that is at the 0 crossing, so there will be some phase reversal in the modulated wave, and hence the envelope of DSB-SC modulated wave is different from the message signal. So as we have discussed earlier, so whenever there is a phase reversal, there will be some envelope distortion, and hence for this DSB-SC wave, the envelope of, if we track the envelope of this DSB-SC modulated wave, will not get the message signal exactly. So the envelope of DSB-SC wave is different from the message signal, because there will be phase reversals occurring whenever the message signal crosses 0. So if we see the time domain waveforms, so this is the message signal and this is the DSB-SC modulated wave. So if we take some signal as a carrier, so if we multiply this high frequency carrier with message signal, so this will be the DSB-SC modulated wave. So we can observe here at 0 crossings. At 0 crossings, there will be some phase reversals since the message signal is suddenly changing from positive value to negative value. So when the carrier is multiplied, so there will be 180 degrees phase shift at the 0 crossings. So this is how our time domain representation of DSB-SC wave looks like. And now in order to find the frequency domain description of DSB-SC, so we can take the Fourier transform on both the sides of this time domain equation. So by taking Fourier transform on both sides of the time domain signal S of t, so S of t is expressed as AC cos 2 pi FCT, that is carrier multiplied by message signal M of t. And from Fourier transform properties, we know that, so if M of f is the Fourier transform of M of t, then the Fourier transform of M of t into cos 2 pi f naught t will be 1 by 2 times M of f minus f naught plus M of f plus f naught. So by using frequency shifting property, so if M of f is the Fourier transform of message signal, so when it is multiplied with cos signal, so this cos can be expressed as e power minus j 2 pi f naught t plus e power j 2 pi f t. So by using frequency shifting property, so this Fourier transform will become the baseband spectrum shifted in frequency by f naught. So it will be 1 by 2 M of f minus f naught plus M of f plus f naught. So the Fourier transform of this quantity will be, so since here M of t is being multiplied by cos 2 pi fct, so its spectrum M of f will be translated in frequency domain by plus or minus fc. So the frequency domain description will be AC by 2 M of f minus fc plus M of f plus fc. So where S of f is the Fourier transform of modulated wave S of t, and M of f is the Fourier transform of message signal M of t. And when the message signal is band limited to the interval minus W to W, then the modulation process simply translates the spectrum of baseband signal by plus or minus fc. So if the message signal is occupying the frequency band from minus W to W, so this DSB-SC modulation will simply translate the spectrum of baseband signal, that is M of f by plus or minus fc. Here, if M of f is the frequency spectrum of message signal, which is occupying the frequencies from minus W to W, and at 0, it will be having maximum value, which is M of 0. So if this is the message spectrum, so the DSB-SC spectrum will look something like this. So the same spectrum will be shifted by frequencies plus or minus fc. So when it is shifted by fc, it will be shifted to the right, and it will be centered around fc. And similarly, its mirror image will be present at minus fc. And here this peak value will be 1 by 2 AC m of 0. So here at f equal to fc, this one will be m of 0 into AC by 2. And the transmission bandwidth required by DSB-SC modulation is same as that for standard AM. So if W is the bandwidth of the message signal, then the bandwidth of standard AM wave is 2W. Similarly, the bandwidth of this DSB-SC wave is also 2W, because it is the bandwidth is the difference between maximum frequency component and the minimum frequency component. So here maximum frequency component is fc plus w, and minimum component is fc minus w. So if we take their difference, then we'll get bandwidth as 2w. So DSB-SC wave will be having the same bandwidth as that of standard AM wave. But however, the carrier is suppressed in DSB-SC, as there are no delta functions at plus or minus fc. So the main difference between the standard AM wave and this double sideband suppressed carrier is that we can observe that here at f equal to fc and f equal to minus fc, the delta functions have been removed. So in standard AM wave, there will be carrier components in the form of delta functions at f equal to fc and f equal to minus fc. But in this DSB-SC, these carrier components are removed. So if we compare these two spectrums, this is the spectrum of standard AM wave, and this is the spectrum of DSB-SC wave. So if we observe here, the standard AM wave has a delta function at f equal to fc and f equal to minus fc. But in this DSB-SC, so here this component at fc and minus fc has been removed. So these components are actually related to the carrier frequency. So we are suppressing the carrier component in the DSB-SC. Hence, it is named as double sideband suppressive carrier. So hence, by removing these carrier components, we can save the amount of power. So since in this standard AM wave, most of the power is used by carrier. So when we are suppressing or removing these carrier components, the total power can be used by this upper and lower sideband, and transmission efficiency can be improved when we are using DSB-SC. But when coming to the bandwidth requirement, both the standard AM wave and DSB-SC wave require bandwidth of 2 into W. So they require the bandwidth which is twice the bandwidth of message signal. So this is how the frequency domain and time domain descriptions of DSB-SC wave. So coming to the time domain description, it is simply the product of message signal and carrier signal. Coming to the frequency domain description, so the same message spectrum will be shifted to the right and left by frequency fc.